students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, today we are going to do part 2 of Thermodynamics chapter where we will be discussing about enthalpy. Okay, how to calculate enthalpy, what are the different types of enthalpy, so everything will be discussed. So please watch the complete video so that you can practice questions and you can understand these concepts very well. Okay, and you can join our WhatsApp channel, link is there in the description section. So this will help you to get access to our PDF notes and mock test and solutions as well. Okay, so now coming to this, how are we going to cover this chapter? So we have already completed part 1 where we discussed about the important thermodynamic terms and its applications. Next, that is today's class, we are going to discuss enthalpy change or reaction enthalpy and enthalpies of different types of reactions. Okay, and then in the third part, in the next class, we are going to discuss spontaneity and gives free energy. Okay, so now coming to weightage, you can see one question you can definitely expect from this particular chapter every year, and it is very scoring if you have remembered the reactions. Okay, sorry, formulas. Okay, so coming to enthalpy change of reactions, in this we have, like, see, first of all, when I'm talking about enthalpy change of reactions, so we have here, first of all, that is one second, yeah, first we have standard enthalpy of reactions. One second. Okay, so first we have here standard enthalpy of reaction. What is standard enthalpy? Then we'll discuss about enthalpy change during phase transition, then enthalpy of formation and Hess's law. Okay, these are the 4 topics that we will cover. And then we have enthalpies for different types of reactions. So what are the different types of reaction? Combustion, atomization, bond enthalpy, lattice enthalpy and enthalpy of solution. Okay, so these all things we are going to discuss in detail. So please continue, watch the complete video. Okay, fine. So now coming to the first thing, that is enthalpy change of a reaction. Okay, so enthalpy change accompanying a reaction is called as reaction enthalpy. Whenever a reaction takes place, either energy is absorbed or energy is released. Okay, so calculation of this enthalpy, this energy, that how much energy is released or how much energy is absorbed during this particular reaction is called as enthalpy reaction or reaction enthalpy. Okay, and next, so this is denoted by this symbol, that is delta HR. Okay, now this reaction enthalpy formula is the enthalpy of products, okay, minus the enthalpy of reactants. Enthalpy the products minus the enthalpy of reactants, where AI, BI are the enthalpies of AI, BI are your coefficients. Okay, so now I'll give you example for this one. Okay, so first we will see here what is standard enthalpy of reaction. Okay, this is very, very important. See here, the standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substance are in their standard states. Okay, when the reactants and products are in their standard state and you are calculating the enthalpy of that particular reaction, we call it standard enthalpy of reaction. Now what do you mean by the reactants and products are in their standard state? The standard state of a substance at specified temperature is its pure form at 1 bar. Okay, so the state of the system, the compound or the reactant or the product should be in its pure form, and the pressure should be 1 bar and temperature should be 298 Kelvin. Okay, so here you can see standard enthalpy symbol is given by delta H naught. Okay, so now okay, one second. Okay, so here I'll be telling you, like, for example, suppose you have a very simple reaction of H2 plus O2 is giving you H2O. Okay, so now if I want to write this reaction, okay, I can, it's like this. Okay, so now you can see the enthalpy of this particular reaction will be called as standard enthalpy of reaction if H2O2 and H2O are in their standard states. Okay, like for example, if I want to calculate C plus O2 giving me carbon dioxide. Okay, now we can also write CO plus half O2 is equal to carbon dioxide, right? But which reaction will give you the standard enthalpy of formation? Now see, here the elements are in their standard state, right? But here carbon CO is not in the standard state. Carbon can exist independently. It doesn't have to exist always with O, right? So this is not the standard state of carbon. but this is the standard state of carbon. So this reaction, whatever is the enthalpy calculated, that will be called as the standard enthalpy of reaction. Clear? Okay, next we have now enthalpy change during phase transformation. Okay, so you know phase transformation, solid to liquid, liquid to gas, solid to gas. So we have different enthalpies named for different phase transformation. Okay, so the first one is your enthalpy of fusion. And what is it? When you melt 1 mole of a solid substance and it is in the standard state, it is called as enthalpy of fusion. It is denoted by delta H fusion. Okay, next we have enthalpy of vaporization. So what is enthalpy of vaporization here? Heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure. Okay, so when you are vaporizing 1 mole of a liquid, temperature is 298, pressure is 1 bar. At that time, whatever enthalpy heat is required, that is called as enthalpy of vaporization. Okay, now similarly we have enthalpy of sublimation. So change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and pressure of 1 bar. Okay, so that is called as the enthalpy of sublimation. Okay, so till now what we understood? First we understood what is reaction enthalpy. Reaction enthalpy is the total energy released or absorbed during a chemical reaction. Now what is standard enthalpy? Second point, standard enthalpy is when this reaction occurs under standard state, standard conditions, whatever energy is released, that is called as standard enthalpy. Now what do you mean by standard state? The reactants and products should be at a pressure of 1 bar, temperature should be 298 Kelvin, and they should be in their pure form, right? So as we saw like carbon dioxide, when it is CO, it is not a standard state, it is not in the pure form, right? Okay, next we saw about the enthalpies of phase transformation. We have 3 types: fusion, vaporization and sublimation. Okay, next coming is standard enthalpy of formation. This is very important. What is standard enthalpy of formation? The standard enthalpy change. Okay, standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable state is called as standard molar enthalpy of formation. Standard enthalpy change for the formation of 1 mole of a compound. This is very important. 1 mole of a compound should form. Okay, now for example, if I want to write the enthalpy of formation of water, okay, so I can write like this: H2 plus half A2O2 gives 2H2O. Right? If I balance this reaction, this is the correct form. The another form is H2 plus half O2 is giving you H2O. Now suppose the question is asked, out of these 2 reactions, which reaction tells you about the enthalpy of formation of water? The answer to this will be this one. Why? Because here you see 2 moles of water is formed, but whenever we calculate enthalpy of formation, it should be always 1 mole. The product should always be 1 mole. For formation of 1 mole of water, how much energy is required or how much energy is released? That is called as enthalpy of formation. Okay, this is very important definition. Please remember this one. For the formation of 1 mole of a compound from its element in their most stable state. So this one should be in their most stable state. Okay, is called as standard molar enthalpy of formation. Now it is denoted by delta HF. Because standard is there, this naught will be there, and then you have delta HF. Okay, next coming to sorry, one second. Yeah, next we have Hess's law. Okay, what is Hess's law here? This is very important. Hess's law tells you about that if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. This definition is very lengthy, but we can easily understand through an example. Now see, suppose I have this one, A to B, okay, one second, we have like this, yeah. So A to C, C to D, D to B. Okay, so suppose I can go from A to B is the enthalpy of reaction. Okay, the final product is A converting to product. Now suppose this reaction A to B is fine, is going like this. First it converts to C, then C converts to D, then it converts to B. This A to B is your enthalpy of reaction. This one is suppose H1 and this one is suppose H2. Okay, H1 and H2 suppose. Then I can say that yeah, and this one is H3. Okay, then we can say that the delta HR is equal to H1 plus H2 and plus H3. Okay, so if a reaction takes place in multiple steps, the overall enthalpy of the reaction will be the sum of the enthalpies of the intermediate steps. Okay, this is very important and most useful and asked questions. Okay, so now you can see here the second topic we are going, types of enthalpies of reactions. Okay, different types of enthalpies are there. The first one is enthalpy of combustion. Okay, so what do you mean by enthalpy of combustion? When 1 mole of a substance, this is also very important, 1 mole of a substance undergoes combustion and all the reactants and products are in the standard state at specific temperature. Okay, so 1 mole of a substance should undergo combustion, means it should react with what? Oxygen. Okay, and enthalpy of combustion is always exothermic. Okay, energy is released in this case. This is also, you should remember, it is exothermic process. Now for example, you can see the combustion of C4H10 is taking place, right? Here you see, here in the case of combustion, the reactant should always be 1 mole. Okay, 1 mole of C4H10 is reacting with this much oxygen to give you carbon dioxide and water. Enthalpy of combustion is -2658. Means when this 1 mole of C4H10 is undergoing combustion, this much energy is released. Okay, next we have okay, so there is a question here to practice for all of us, right? Calculate the heat of combustion of ethane in the reaction. You have been given C2H6, so I will write the reaction here. So we have C2H6 plus 7/2O2 gives you, okay, 2 CO2 plus 3 water, 2 CO2 plus 3 water. Okay, now question is, you have been given with formation of ethane gas, so you have been given with delta HF, one second, yeah, you have been given with delta HF of ethane, that is C3H6, that is how much? Then we have carbon dioxide, so first let me write down all the values. Okay, next you have delta H of carbon dioxide, water, liquid. Okay, fine. Now let us write down the values. We have -84.7 here. Okay, and next we have -393.5. Okay, and then we have -285.8. Okay, here while solving the questions you should remember that enthalpy of formation, okay, for elements in their pure form is considered to be 0. Okay, so that means suppose for example carbon is found as carbon in the nature, so the enthalpy of formation of carbon will be 0. Oxygen is naturally found as O2 in nature, so enthalpy of formation of O2 will be equal to 0. Okay, so now if we solve this question here, so if you remember, delta H of the reaction is equal to delta H of product minus delta H of reactants, right? So what are the products here? Carbon dioxide and water. So we have delta H of reaction will be 2 times of enthalpy of carbon dioxide. So I'll write 2 times of, first let me write down the enthalpy of formation of carbon dioxide plus 3 times of water, 3 times of delta HF of water. Okay, this is over for products, minus reactants we have C2H6 only, so delta H not F of C2H6. Okay, and O2 enthalpy is considered to be 0. So now if I substitute the values, 2 into CO2 is -393.5. Okay, then I have plus 3 times of one second, here I have written wrong, we will not write the values now. Okay, I have just written the substitution. So 3 types of enthalpy of formation of water. So that is 3 into minus 285.8. Okay, so this is over for products, right? Then minus enthalpy of reactant. So C2H6 is C3H6 is minus C2H6 only, sorry. Yeah, C2H6 is minus 84.7. Okay, this is done. Now if you calculate this one, okay, if you solve this numerical value, you will be finding that the answer will be somewhere around minus 1559.7 kilojoule per mole. That tells you that if you burn 1 mole of ethane gas, this much energy will be produced. Okay, fine. So enthalpy of combustion done. Next we have enthalpy of atomization. So what is enthalpy of atomization? See, enthalpy change to break 1 mole of bonds completely to obtain atoms in the gas phase. When you are breaking 1 mole of a compound so that you get atoms out of it, okay, that is called as enthalpy of atomization. Now if you see here CH4, okay, now if you break this carbon and hydrogen, all the bonds, then you will find what? Carbon and 4 hydrogen atoms, right? So this is called as enthalpy of atomization, 1665 kilojoule per mole. Okay, so enthalpy of atomization means to get atoms out of this compound, how much energy is required. Okay, fine. Next we'll go to bond enthalpy. Now bond enthalpy is of 2 types. Okay, one is direct bond enthalpy. So what is bond enthalpy? Change in enthalpy or change in energy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form the products in the form of gas. When you are breaking 1 mole of a compound to get atoms or to get the atoms or the elements in the gaseous form, that is called as bond enthalpy. Now there is not much difference in case of atomization enthalpy and bond enthalpy for diatomic molecules. Okay, so for example, if I have like this here, yeah, suppose H2 is breaking to give you 2H. Here the bond dissociation enthalpy or bond enthalpy and the atomization enthalpy, both are same thing because you are breaking it to get atoms in terms of gaseous form, right? So that is what is bond enthalpy. But there is something called as mean bond enthalpy also. Now what is mean bond enthalpy? Average amount of energy required, average, okay, to break 1 mole of bonds of a specific type in a chemical compound. Now why this average bond or average enthalpy term is there? Now if you see, just now we have seen carbon, if you break CH4 will get C and 4H, and the enthalpy of atomization is 1665 kilojoule per mole. Okay, so that means in this molecule what exactly we are breaking? If you see, we have 4 CH bond. If I break this 4 CH bond, I will get carbon and 4 hydrogen, right? And to break this, I am getting around 1665 kilojoule per mole energy is required. Okay, positive is there. So if I give this much of energy, then this carbon and 4 hydrogens will be produced. But how is it this exactly happening? First 1 bond will break, second another bond will break, then third bond, then fourth bond. At a time all the bond do not break. Okay, so now if you see here, we see that the amount of energy required for different CH bonds are not same. When you break the first bond, okay, energy required is around 427. When you break the second bond, 439, then 452, and for the last bond it is 347. So when you see, we are breaking the same CH bond of the same compound, but energy required are different. So that is why in this type of case we need to find the average bond enthalpy. So the total energy was 1665 that was required, divided by 4, and you will get 416 kilojoule per mole. Okay, which is nearly equal to these all individual values. So average bond enthalpy is required in case of polyatomic molecules. Clear? Okay, next, bond enthalpy we can also use to calculate the enthalpy of a reaction. So enthalpy of a reaction, if you want to calculate, it is bond enthalpy of products, here I'll make bond enthalpy of reactants, okay, minus the bond enthalpy of products. Okay, Bond enthalpy of reactants minus bond enthalpy of products will give you the enthalpy of the reaction. If you have formation enthalpy, then enthalpy of reaction is formation enthalpy of products minus formation enthalpy of reactants, the first question that we did. But if it is asked in the terms of bond enthalpy, it is reactants minus products. Okay, we can see a question from here. Okay, the question is, calculate the carbon-carbon double bond energy in the ethane from the following reaction. Okay, so the reaction is given, C2H2 plus H2 gives CH3, delta H of the reaction is given, bond enthalpies are given. Okay, so now if you see C2H2, we have structure like this. Okay, so what are the bond enthalpies involved here? Let this carbon-carbon double bond we have to find out, let it be X. And we have CH bond, how many CH bond? We have 4 CH. So the enthalpy, bond enthalpy of, so if I want to calculate the delta H of the reaction, that will be equal to bond enthalpy of, okay, C2H2 plus, then we have bond enthalpy of H2, okay, bond enthalpy of H2, then minus I have bond enthalpy of CH3, bond enthalpy of CH3 and CH3. Okay, now bond enthalpy of C2H2 is what? X plus 4 CH bond, right? So we have CH bond is 412 and CC bond is X. So I can say that this first value is how much? First value is X plus 4 into CH bond is 412. Okay, next I have bond enthalpy of hydrogen. What is the bond enthalpy of H2? In this there is only one H2 bond, so that is 436. Okay, minus bond enthalpy of CH3. So if you see the structure of CH3, okay, it is like this. So there is one CC bond and we have 6 CH bond. So CC bond is 348. So that is 348 plus 6 times of CH bond is 412. Okay. Now this is equal to the enthalpy of reaction, which is given to you as minus 138. Now here you have to see the units, all are in kilojoule per mole, right? The bond enthalpies are also kilojoule per mole, so there is no problem, we can put kilojoule per mole. Okay, so now if you solve this, you will be getting the X value as somewhere 598. Okay, so the correct answer for this question will be option number D. Okay, you can check the calculation, but this is just the method how to solve it. Okay, next we can go to lattice enthalpy. So what is lattice enthalpy? See, when an ionic solid, okay, breaks into its gaseous constituent atoms, the energy that is required is called as your lattice enthalpy. Enthalpy change occurs when 1 mole of an ionic solid dissociates into ions in gaseous state. So if you see NaCl solid breaks to give you Na plus gas and Cl minus gas, that is called as your lattice enthalpy, 788 kilojoule per mole. Okay, now this lattice enthalpy cannot be calculated directly. Okay, so to calculate the lattice enthalpy, we need something called as Born-Haber cycle. Okay, now see, what is Born-Haber cycle? Now this is an example of Born enthalpy cycle to calculate the lattice enthalpy of NaCl. Now how exactly NaCl is formed? So first step is what? See here. First what happens is sodium, okay, where we have sodium, one second, okay, we need first is your, yeah, so we have here sodium solid, okay, the first sodium solid. Sodium is converted to sodium gas, for that we need sublimation enthalpy. Okay, next sodium gas is converted to Na plus ion, for that we need ionization enthalpy. Okay, now this, okay, now this what happens for chlorine, what happens for chlorine gas? So similarly, if you see, this chlorine gas is first converted to from where we have chlorine gas, one second, yes, now this chlorine first breaks half of bond dissociation enthalpy. Okay, this is for chlorine. Half of bond dissociation enthalpy we get here Cl ion, Cl gas. Okay, it produces Cl gas. You can see Na gas is produced and now we have Cl gas. We need to convert it into Cl minus, so we have electron gain enthalpy, negative value is there, and now we get Na plus and Cl minus. Okay, so till now if I say what are the process involved, first we have delta H of sublimation for sodium. Then we have delta H of ionization energy. Okay, then we have delta H of Cl2. We are breaking this, so for that we need half of Cl2. Okay, then we have delta H of electron gain enthalpy to convert it into Cl minus ions. Now this Na plus and Cl minus, okay, will come together to give you NaCl solid, and that is where the lattice enthalpy plays a role. Okay, now these all things will be equal to what? Enthalpy of formation of NaCl, right? We are forming NaCl here. What is the exact reaction happening? Na solid, okay, plus Cl2 gas is giving you NaCl solid. In between that we have so many steps, that is first we are converting Na to Na gas, then you are converting Na to Na plus gas, here you are converting Cl2 to Cl gas, and then you are converting Cl to Cl minus gas. Now these two are reacting to give you NaCl, right? So now this value is known to you, this value known, this value known, this value known, this value known, this value we need to calculate, right? So these all values are written here, you just need to calculate the lattice enthalpy. So this way of calculating the lattice enthalpy is called as Born-Haber cycle. Okay, so now we will go to the next thing, that is enthalpy of a solution. Okay, so solution, how, like when a solute dissolves in a solvent, okay, some energy is released, that is called as enthalpy of solution. Okay, so how do you see here? You can see AB is a solid. Okay, now AB first breaks into its gaseous ions A plus and B minus. Okay, A plus gas and B minus gas. So what is the energy required there? Lattice enthalpy. Then A plus and B minus gets converted here in the gaseous form to aqueous form, and that is your hydration enthalpy. Okay, so lattice enthalpy can be, or enthalpy of a solution can be given as lattice enthalpy. Okay, lattice enthalpy plus hydration enthalpy. Okay, so that's all. Now here is a question for all of you. This was a homework question. The value of the product of a universal gas constant and temperature RT is 10 kilojoule per mole. Number of moles is 1 mole. Okay, internal energy is your 20 kilojoule. Then you need to calculate the enthalpy of the reaction. So we have this one, delta H is equal to delta U plus delta Ng RT, right? Now delta H value you need to calculate, delta U value is 20 plus RT is 10, so we will get 30 here. Okay, so the correct answer for this question was option number A. I hope all of you would have solved it. Now let us see today's sum question. So this is your question number 1. Okay, so on the basis of thermodynamical equations A, B, C, find out which of the algebraic relationships given in options 1 to 4 is correct. Okay, so we have to find which of the reactions is correct. Okay, so now if you see here, in this equation, first equation, there is no Cu, right? But in the second equation, but in the second equation I have CO, and in the third equation I have CO. Now if I add these two equations, B plus C, if I just add B plus C, what will I get? CO will get cancelled, right? Half O2 plus half O2 will become 1 O2, so I will get C plus this one is O2, and then this side I have CO2, right? Now this one will be equal to Y plus Z, right? You have added B plus C, so it is Y plus Z. So I can say that reaction A is equal to B plus C, right? So I can say that X is equal to Y plus Z. So the correct answer for this question will be option number 3. Just you have to find out which two reactions you can add to get the correct answer. Okay. Next, if we see here, consider the reactions given below on. So this is your question number 2. Okay. Find out which of the following algebraic relations given in options 1 to 4 is correct. Okay, so you have carbon plus 4 hydrogen gives CH4, and that is your x kilojoule per mole. Okay, and here you have C graphite solid state and 2H2 in the gaseous state, and CH4 is formed. Okay, and here we require Y. Okay, so in which case which value is more? Okay, now here see here, now this 4H in the gaseous state would not have been produced directly, right? How would have been this one will be produced? For first H2 will break to H, right? After this bond dissociation enthalpy has taken place, then only we would have got 4 hydrogen, right? And also carbon is in the solid state here, which is found naturally, but here carbon is found in the gaseous state. That means this also involves one step here, carbon solid to carbon graphite, carbon gas, right? So that you see that here what happens, the reactants, okay, are not in the native state. We need to provide some energy to first bring them to this state, and then this one is forming. Okay, some x kilojoule is required, but here the elements are already in the natural state, so definitely here more energy will be required. So x will be greater than y, that is option number 3 here. Okay, next is question number 3. In case of decomposition of hydrogen molecule into 2 hydrogen atoms, the enthalpy of atomization is same as the enthalpy bond dissociation enthalpy. I told you bond dissociation enthalpy for diatomic molecules will be same as the atomization enthalpy. Okay, here also you are breaking one bond, there also you are breaking one bond. Okay, next, enthalpy of combustion is always negative. Okay, it is always a exothermic reaction. Next we have a homework question here. Combustion of glucose, okay, takes place according to the following equation. Delta H is given to you. Energy required for the production of 1.6 gram of glucose is, okay, how much will be required, how much energy is required for the production of energy required for the production of 1.6 gram of glucose is, okay. So I think energy required for the combustion, okay, for the combustion you need to calculate for the combustion of 1.6 gram of glucose. So how much gram will be required for the combustion of 1.6 gram of glucose, that you need to calculate. Okay, so try this question and put your do not forget to comment down the answers. So that's all in this lecture, students. I hope you would have enjoyed this class, and if you have any doubt, please comment down. I'll definitely address it. And thank you for watching. Please subscribe the channel for more such updates.